This is the third of 4 videos to accompany the Further Mathematics conference session, Getting a Feel for Further Mechanics. In this video, we will start to include the ideas of collisions. First of all, we will recap the idea of conservation of momentum, which is likely to be familiar to many students from their GCSE science work, and possibly also to many teachers, as this concept used to be on the single A-level course, although it is now only in further mathematics syllabuses. Here we have an example of two balls colliding, and there is a diagram showing their momentum before and their momentum after, where momentum is the product of the body's mass and its velocity. Conservation of momentum is a very important idea and can be used to determine different things before and after collisions. In many questions about momentum, often quite a lot of information is given. For example, in this situation, we might be given the mass of both balls, both initial velocities, one of the subsequent velocities, and then be asked to find the missing final velocity. In reality, this is quite a complicated situation, and lots of different things could happen. For example, in this case, we can see that the balls start by moving towards each other and then move off in the same direction afterwards. But this isn't the only possibility. A simple momentum question would give you lots more information than you'd probably get in real life. Before we go any further, let's look at a simple practical task that students can do to help them get a sense of what is possible when two balls collide. In the pack of resources for this session, you will find a set of bingo cards. Students, probably working in pairs or threes, should be given one of these cards and asked to explore which of these scenarios is possible. The cards are mixed up, and so students will have different cards to their neighbours and therefore different scenarios to investigate. In addition to the cards, students should be given a ruler to act as a track and a selection of balls to roll along it. If possible, provide a variety of different types of balls, such as hollow balls and solid balls, marbles, bouncy balls, possibly things like ping pong balls, just to get a variety of different possible scenarios. Where possible, try to make it so that the radii of the ball are as close as possible to each other. Students should roll the balls along the track according to what the first part of their bingo card says and see what different situations they can engineer for the result. They should focus on what happens immediately after the collision, because it's possible that, for example, a ball might start rolling in one direction and then roll back. The ruler helps to make sure that the centres of the balls are aligned as they roll. Students can then explore, using their bingo card, which situations are possible and get a sense for how different types of ball might interact with one another depending on their composition and the velocities that they begin with. A further idea in this topic is that of coefficient of restitution, which gives us more information about how the two different balls will interact with one another. Here is a formula for the coefficient of restitution, although in many cases it's easier to think of it as the speed of separation divided by the speed of approach. Here's an example. We had before our situation where the two balls were approaching one another and then travelling off in the same direction afterwards. If we apply this formula for the coefficient of restitution to this situation, we see that we get a value of E of 1 over 14. We need to be very careful with these sorts of calculations. Negative sign errors are in abundance here, so study this calculation carefully if this is a new topic for you, to make sure you understand the sign of each number in the calculation. The value of E will determine the nature of the relationship between the two balls and what will happen after they collide. It is important that further math students have a sense of what the value of E can tell them in a given situation. As before, the practical experiments can help here, particularly with finding out particularly important values of E, such as when E is 0 or when E is 1. Students can also use software such as Geogebra to explore collisions. Here we have two balls of equal masses and equal radii, and I can vary, using these slider controls, their initial velocities and also the coefficient of restitution between the two balls. By pressing Start, I can see what happens in the collision. I can then vary my value for E to see how that affects what happens. In this case, they were moving toward each other and then moved off in the same direction afterwards. Let's see what happens if E changes to 0.2. Here we can see that A comes to a standstill and B moves back in the opposite direction to where it began. If I change E again, this time to 0.3, we can see that now A rebounds and goes in a different direction to its initial direction of travel. So three different values of E, quite close together, cause three very different results. As mentioned, it's important that students are particularly familiar with what happens when E is either 0 or 1. In the case where E is 0, we would describe this as a perfectly inelastic collision. Watch what happens. Here we can see that the balls move off together. The speed of separation is 0 here, therefore they must have the identical velocities. We sometimes refer to this as coalescence. If E equals 1, we have a perfectly elastic collision, which means that no kinetic energy is lost. As you can see, the initial velocity of particle B has transferred to A and vice versa. Now let's link this to our swinging ball experiment. You can see that I have changed the velocity of B to be 0, therefore B begins stationary. I have fixed the value of E as 0.5, and I'm going to vary the initial speed of ball A. Watch what happens to the relative speeds of A and B after the collision. Here we can see that the speed of A is 0.75 and B is 2.25. I shall repeat that for a different value of the initial speed of A. And again. What you will hopefully have seen is that in every case the speed of B after the collision is always 3 times larger than the speed of A, and is therefore proportional to it. Let's think about what this means in the case of our swinging balls. Earlier on, when we investigated this situation, we were not sure about the interaction between the red and yellow balls when they connected. We wondered how much of the initial speed of the red ball would be transferred to the yellow ball upon impact. But as we have seen, regardless of the value of E, we know that the speed of the yellow ball will be proportional to the arrival speed of the red ball. Therefore, students might now want to discuss whether they are convinced that the horizontal distance d will be proportional to the square root of the height h.